Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, check out the links in the description below. So now we're just going to get started on our set of questions for today. Okay, so the first question asks, what is the net ionic equation for the reaction between lithium carbonate and calcium chloride? Okay, so when we answer, when we try to find out the net ionic equation, first we want to write out the reaction that occurs. So I'm going to write down my lithium carbonate first, and then it reacts with calcium chloride. And typically what happens is a double displacement reaction. So our lithium will then be bonded with the chlorine. So since lithium has a +1 charge and chlorine has a -1 charge, they will react at a 1-to-1 ratio. And then similarly, calcium has a 2+ charge and carbonate has a -2 charge, so they will also react at a 1-to-1 ratio. I'm also just going to look up the different solubility rules, and we want to do this in order to determine whether or not our calcium carbonate will dissolve in water. Okay, so basically when you have calcium with a carbonate, I don't know if you can read that. So basically compounds that contain carbonate are insoluble except when they're bonded with NH4+ and the alkali metal cations. So since calcium is not an alkali metal, therefore this compound is insoluble. So it won't be aqueous, it will be solid, and it will be the precipitate in the reaction. So after we find out which one of the compounds is insoluble, we want to make sure that this reaction is balanced. So first, let's look at the lithium. You'll notice that on the left side, there are 2 lithiums. So I'm going to put a coefficient of 2 in front of my lithium chloride. Similarly, for the calcium chloride, there's a subscript of 2 where the chlorine is. So this also works to put the 2 in front of the lithium chloride. And then we just want to make sure that the rest is balanced, and it is. So after we write down like the full equation, we are going to write down the ionic equation. And basically what that means is that we are going to separate all of the compounds that are aqueous into their ions. And also we want to make sure that everything is balanced. So we have the lithium carbonate breaking up into 2 lithium ions. A CO3 2- ion. And then for the calcium chloride, this is going to break up into calcium 2+. plus 2 Cl minus. I'm going to draw the rest on the second line so that there's more room. Okay, so we have 2 lithium plus. Just want to make sure I label these all correctly. Plus 2 chlorine. And the only one that doesn't separate into its ions is the solid calcium carbonate. So I'm just going to keep this as CaCO3S. And now, after we write down the ionic equation, we want to remove any spectator ions. So basically, these are the ions that are the same on both the reactant side and the product side. I'm just going to say ions that can be canceled out. So let's look at our reactant side. There's 2 lithiums and 2 lithiums on the product side. So this is an example of a spectator ion. And then again, we have 2 chlorine ions and then another 2 chlorine ions that will cancel each other out. So finally, after we remove all the spectator ions, we can write down the net ionic equation. So this is what the question is looking for. You can see that it's like a multi-step question. So after we remove the spectator ions, all we are left with is a carbonate and then a calcium. And then we also have our precipitate, calcium carbonate. Okay, so this is our final answer. So let's see what the junior tutor said. To answer this, let us go from the molecular equation to the complete ionic equation, and then lastly to the net ionic equation. The molecular equation and complete ionic equation both show all of the species in the reaction. The difference is that in the complete ionic equation, strong electrolytes are shown as ions. So in our case, a strong electrolyte was like the lithium carbonate and the lithium chloride. If we have a strong acid, it will be shown as H+ and its conjugate base. The molecular and complete ionic equations are shown in equations 1 and 2 respectively. So here they have the same molecular equation that I have in black, and then you'll see that they separate into their ions for equation 2. So we see that the reaction is a double displacement reaction where lithium and calcium displace each other to form 2 salts. The net ionic equation is a way of representing a chemical reaction where only the ions that are directly involved in the reaction are shown. The spectator ions, or ions that do not participate in the reaction, are omitted. And another way of looking at net ionic equations is that the species that appear in both the reactant and product side of the equation cancel each other out. This means that lithium plus and chlorine minus are omitted from the equation, and this is shown in equation 3. This is a very well written answer, so this solution is correct. Okay, so now let's move on to question number 2. If the amount of radioactive phosphorus 32 used to treat leukemia in a sample decreases from 1.2 milligrams to 0.3 milligrams in 28.6 days. What is the half-life of phosphorus 32? Okay, so this is question number 2. First, I'm just going to write down everything that we know. We know that our initial mass is 1.2 milligrams. And we know that our final mass is 0.3 milligrams. And we also know that the time that it took to get to 0.3 milligrams was 28.6 days. And they're asking what the half-life is. So I'm gonna show a method because I can already see the junior tutor answer and it looks like that is going to give you the correct answer. But I'm just also gonna do a separate method that could potentially help answer. So we can try to break it up into parts. Like let's say half of 1.2 milligrams is 0.6 milligrams. And then half of 0.6 milligrams gives you the 0.3 milligrams. And we know that this whole process took 28.6 days. So all we have to do is find out how many days it took for the phosphorus to get to 0.6 milligrams. And it should be the same amount of days that it took to get to 0.3 milligrams. So all I'm gonna do is do 28.6 days. And then I'm gonna divide that by 2, since I know that this process happens twice. And that's gonna give us x. So x is equal to 14.3 days. And this is the half-life of phosphorus 32. Okay, so let's see the answer from our junior tutor. The nuclear half-life expresses the time required of a sample to undergo radioactive decay. Exponential decay can be expressed mathematically as AT is equal to A naught times half to the power of T over half-life. So AT is the amount of substance left at the time. A naught is the initial amount of substance that will undergo decay. T is the time in question. And then T half is the half-life of the decaying quantity. So this is your standard equation when you want to answer a half-life equation question. I just showed a different type of method that you could do, but this is definitely the way to go when you want to try to solve half-life reaction equations, especially if it's not as simple as like two half-lives to make 0.3 milligrams. This is definitely the way to go. So in the problem, the given are the amounts of substance left, the initial amount of the substance, and the time in question. The only unknown in the equation is the half-life. So you see that all they do is plug in all the values that they're given. So 0.3 milligrams is what they're left with. The 1.2 milligrams is how much we started with. The T is 28.6 days. And then we're trying to solve for half-life. So if you simplify and try to solve for the unknown, you end up with T half is equal to 14.3 days. And we know that this is also what we got, so we can confirm that this solution is correct. Okay, moving on to question number 3. Estimate the reaction enthalpy for the production of SF6 gas from SF4 gas, given that the bond enthalpies in F2 and in each of SF4 and SF6 are 158, 343, and 327 kilojoules per mole, respectively. Okay, so I'm just going to try to write down the reaction for this equation. So we start off with the sulfur tetrafluoride, which is a gas. And then another fluorine molecule is added. And then this creates sulfur hexafluoride, which is also a gas. And then let's just double check to make sure that everything is balanced, since that is good practice. And you'll see that it is. We have 1 sulfur on the left, 1 on the right, and then 6 fluorines for the reactants and 6 fluorines on the right. So now I'm just going to write down all of the different enthalpy values that they gave us in the question. So the symbol for enthalpy is delta H, and they give us the bond enthalpies. So I'm going to denote in like the lowercase subscript the enthalpy of the bond of the fluorine-fluorine bond is 158 kilojoules per mole. So this value represents the energy that it takes to form the fluorine-fluorine bond. And then similarly, we can do the same thing. The enthalpy of the SF bond. So the first one is for the sulfur tetrafluoride. And this is 343 kilojoules per mole. And then lastly, I'll write down the enthalpy of the other SF, but this time this is for sulfur hexafluoride, and it is 327 kilojoules per mole. Okay, so now that we wrote out all of our values, I'm going to round out the standard expression that you would use in order to estimate the reaction enthalpy. So to start off, it's going to be delta H of the reaction. And all that is that it's going to be, sorry, that's an ugly sum. It's going to be the sum of your enthalpy for the reactants. And it also depends on how many moles of your reactants there are. So since everything reacts at like a 1-to-1 ratio, we don't really have to worry about it in this case, but that's why I also mentioned that it's important to balance your equations before you start questions like this. And then it's going to be the sum of the enthalpy of the reactants minus the sum of the enthalpy of our products. So now I'm just going to sub in what that means. So people usually get intimidated by the sum symbol, but it's pretty simple. You just realize it just means the sum. So for the first reactant, the sulfur tetrafluorine, the enthalpy value that's given, it is related to only one bond. But since we have 4 SF bonds in the sulfur tetrafluorine molecule, I'm going to multiply that value by 4. I'm just going to write out the variables so that you can see why it's multiplied by 4. And then for the fluorine-fluorine bond, there's only one fluorine involved, so I don't have to multiply anything. It's just going to be our delta H of the fluorine. So all of that is in square brackets, and we're going to minus it by 6 times our product, our enthalpy of the product, which is the SF value for sulfur hexafluoride. And then again, this is going to be multiplied by 6 since there are 6 sulfur fluorine bonds in this molecule. So I'm just going to write it showing all the different values. So it's going to be 4 times 343 kilojoules per mole plus 158 kilojoules per mole minus 6 times 327 kilojoules per mole. And now if we do the math and calculate what this equals out to, we end up getting negative 432 kilojoules per mole. So this is the reaction enthalpy for the production of sulfur hexafluoride. So let's see the answer from our junior tutors. Bond enthalpy is defined as the amount of energy required to break 1 mole of the stated bond. During chemical reactions, the bond between atoms may break, reform, or both to either absorb or release energy. The heat absorbed or released from a system under constant pressure is known as enthalpy, and the change in enthalpy that results from a chemical reaction is the enthalpy of reaction. When using bond enthalpies to estimate enthalpy of reaction, there is a series of guidelines that can be followed in order to make sure that the estimation is correct. Step 1 is to identify which bonds in the reactants will break and identify their bond enthalpies. So that's what we did here in the black. Step 2 is to add up the values for the broken bonds. So that's what we did in the first part of this equation here. And then we want to identify which new bonds form in the products and list their negative bond enthalpies. The negative is used because the energy is released when bonds are formed. Step 4, add up the bond enthalpy values for the formed product bonds. Step 5, combine the total values calculated in step 2 and 4 to get the enthalpy of the reaction. So you see they have the same simplified formula that we saw already. And then they show a neat illustration of how the formation of SF6 occurs. And then they follow out the math the same way that we did and end up with minus 432 kilojoules per mole. This solution is correct. Okay, so now we can move on to question number 4. What is the mass in kilograms of 5.65 times 10 to the 25? I'm guessing like particles or molecules of carbon dioxide. The molar mass of carbon dioxide is 44.01 grams per mole. Okay, so first I'm going to write down what we know. We know that there are 5.65 times 10 to the 25 molecules of CO2. So they gave us the molecules of CO2, and in order to calculate for mass, we want to find out how many moles of CO2 we have. So in order to do that, we are going to use Avogadro's number. Let me write out what this equation would look like. So Avogadro's number is a helpful way of trying to figure out how many molecules per mole that you have for a given like substance. So it doesn't have to be molecules, it can be photons or particles, just depends on the way that it's worded in the question. And its value is 6.022 times 10 to the 23, and then the units are molecules per mole. So in order to calculate the number of moles, all we have to do is do 5.65 times 10 to the 25 molecules divided by 6.022 times 10 to the 23 molecules per mole. And you know that you did it right if your units cancel out nicely, so our molecules will cancel out and our moles will go from the denominator to the numerator. And then we end up with a value of 93.82 moles of CO2. So that's the first part of the question. Well, first part of the answer. The second part, we need to calculate mass. So everyone's favorite equation is mass is equal to the number of moles times the molar mass. So we figure out our number of moles in the previous step. It was 93.82 moles. And they gave us molar mass in the question, which is 44.01 grams per mole. And again, you know you did it right if your moles cancel out and you're left with your desired units, which is grams. So we end up with a mass of 4,129.13 grams. And the question is asking, what is this in kilograms? So then we just have to do our conversion factor, which is pretty much dividing by 1,000. But if you don't know how to do that, then I'll just write it down here. So there are 1,000 grams in 1 kilogram. Let's show the units canceling out. And you get 4.129 kilograms of CO2. Let's see the answer from our junior tutor. Step 1, calculate how many moles are there from the given number of CO2 molecules. So you can see that they divided by Avogadro's number to get 93.82 moles. After finding the number of moles, multiply it to the given molar mass to find the mass of carbon dioxide. So they got 4,129 grams. And step 3, convert the calculated mass to the desired unit, 4.129 kilograms. Okay, so this solution was correct. Now let's move on to question number 5. So it's another kind of stoichiometry-based question. Calculate the moles of ammonia present in a 5.05 gram sample if the molar mass of ammonia is 17.03 grams per mole. So again, mass is equal to 5.05 grams. They already gave us molar mass, which is 17.030 grams per mole. And we're looking for number of moles. So we're going to use the equation N equals mass over molar mass, which is 5.05 grams divided by 17.030 grams per mole. Again, you'll see our units cancel out, and we are left with 0.2965 moles of ammonia. Let's see the answer from our junior tutor. We need to perform dimensional analysis. Recall how to convert from moles to mass using the molar mass. The solution is shown below. And this is correct. Okay, so now let's move on to question number 6. A mixture of copper 2 carbonate and sodium chloride can be separated and recovered using which of the two solvents? Water or acid water? Briefly explain. So this is kind of similar to the first question where we want to find out if copper 2 carbonate or if sodium chloride are soluble in water. So if you remember from the first question, if the carbonate ion, I'll just write this down. If the carbonate ion is not bonded with NH4 plus or a group 1 alkali metal, it is insoluble in water. And let's look at sodium chloride. Sodium chloride is made up of a group 1 alkali metal and also a chlorine ion. So this is soluble in water. If we look at our solubility rules again, so since copper 2 carbonate is insoluble in water and the sodium chloride is soluble in water, then therefore we can use water as a solvent to separate. So to recover, since that's kind of like the second part of the question, we will dissolve the mixture in water, and then this will make our sodium chloride the only one that is dissolved, and our copper 2 carbonate will be a solid. So then we can decant the copper 2 carbonate solid to separate. Let's see the answer from our junior tutor. Mixture can be separated by using water only. This is because of the solubility of copper 2 carbonate and sodium chloride in water. As per the solubility rules, all salts containing alkali metals are soluble in water, while salts containing the carbonate ions are insoluble in water, with some exceptions. So when water is applied to the mixture, the sodium chloride will completely ionize in the solution, leaving the copper 2 carbonate as the only solid particles. All there is to do is to decant the solution to separate the solids from the liquids. The solution is correct. Okay, so let's move on to question number 7. What is the E in 1,1-E-ethene 1,2-diyl dibenzene stand for, and what does it mean? So this is question number 7. First, I'm going to write down the structure of that very long compound they gave us. So the E just is a way for us to determine what side of the double bond the substituents will be on. I can already kind of see the junior tutor's answers, so I'm going to write down this same thing, showing how it separates like that. And then when you have the E, this means that the substituents are on opposite I'll put priority substituents are on opposite sides of the double bond. I think the actual E came from a German word called I don't want to butcher that name, so I'm just gonna not say it. Let's see what our junior tutor said. The E stands for Entgegen, which is the German word for opposite. This denotes that the priority groups are on opposite sides of the plane, which is shown in the dotted line. As seen in figure 1, the benzene groups are on opposite sides of the plane of the molecule. This is why it is denoted as E. Think of this as the equivalent of trans and cis-trans notation. The difference between trans and E is that the EZ notation is not limited to the same group. If we add a bromo group to the compound, we cannot use the cis-trans notations anymore, but we can still use the EZ notation. Okay, so it's very informative, so this solution is correct. Okay, so let's move on with question number 8. Why doesn't the indicator affect titration? So this is because the indicator is the substance that you put in your titration, and it changes color depending on the pH. It also doesn't affect titration because only a small amount is used. So you really only add like 1 or 2 drops of your indicator, such as like phenolphthalein, and that's basically all you need for it to change the color in a titration. So it's pretty helpful. See what our junior tutor said? Indicators are substances that are used in a titration experiment to determine the endpoint of the titration. These substances change color when a certain pH is reached. There are usually weak acids or bases, but their conjugate bases or acid forms have different colors due to differences in their absorption spectra. It does not affect the result of titration because it is usually added in small amount, 1 to 2 drops only, just enough to make a visible color when a certain pH is reached. And as said above, it is a weak acid/base. However, if a large amount of indicator is used, the indicator will affect the final pH, lowering the accuracy of the experiment. So for every titration experiment, it is appropriate to determine the amount of indicator that will be added to the analyte. So you don't want to add too much indicator, like they said, because this will have an effect on the pH. Okay, so let's check out question number 9. What are kinematic equations? So first I'll write down the definition of kinematic, which basically describes the motion of an object. So basically there's different kinematic equations, and these are the 3 main ones. First I'll just write down the most common one, where velocity is equal to the initial velocity plus AT. And then on the right, I'll just write down what everything means. So this is final velocity V naught. Every time there's a subscript of 0, this means like initial. So initial velocity. A stands for acceleration. And Yeah, so t is time. And then I'll write out the other two kinematic equations. You can also have delta x is equal to initial velocity times time plus half a t squared. So I'll also label that delta x. That just stands for displacement. So if your object, I'll just write an example of delta x. It's basically like your final position minus your initial. So sometimes questions will give you two different points and say it started at this point and ended in that one. So that's how you would calculate delta x. And the last kinematic equation is v squared is equal to v naught plus 2a delta x. So depending on what they give you in a question, you can use any one of these three equations to try and solve for your unknown. Let's see the answer from our junior tutor. Kinematic equations are equations that describe the motion of an object. There are three basic kinematic equations, and then they just give the same three that I have. And then where v is the final velocity, v naught is the initial velocity, a is acceleration, t is time, and delta x is the displacement. This solution is correct. Okay, so now let's go on to question number 10. How many quarts are there in 5 gallons? So basically, 1 gallon is equal to 4 quarts. So all we have to do is a conversion factor. So whatever we're looking for, which is quarts, I'm going to denote as x. And it'll always be on top. So there are x quarts in 5 gallons. And then when you do your conversion, on the other side of the equation, you're just going to put the conversion factor. So we know that 4 quarts, there are 4 quarts in 1 gallon. And then if you look at the two sides, what we're looking for, which is x, is on top, and it's both quarts. And what we're looking for, what we're trying to get rid of, is the gallons, which is at the bottom. So if we simplify this and bring the 5 to the other side, you'll notice that the units should cancel out, and that's how you know you converted it successfully. I'm just going to show that we are going to multiply both sides by 5 gallons. And this is what I was talking about with the units. Your gallons should equal out. And then you get x quarts is equal to 20. Therefore, there are 20 quarts in 5 gallons. Let's see the answer from our junior tutor. To solve this, we just need to use the conversion factor. 1 gallon is equal to 4 quarts. Solving this, they just multiplied it out and got 20 quarts. So this solution is correct. The simple unit conversion. Now let's move on to question number 11. This is kind of similar where you just want to use all your different conversion factors. How do you convert milliliters to liters? So in 1 liter, there are 1,000 milliliters. So therefore, to convert milliliters to liters, we need to divide your value by 1,000. Okay, so since this question was kind of short, I'll just give an example. So let's say how do you convert 50 milliliters to liters? Again, we're just gonna put our x on top. X over 50 mils, since we're looking for liters. And then I'm just going to mimic that on the right side. Liters on top. 1 liter is equal to 1,000 milliliters. And then when we solve for x, we multiply both sides by 50 mils. You'll notice that the units will cancel out. And then I also just like to move the decimal if you don't have a calculator handy. Let's say the decimal's here. It's gonna move 3 spaces to the left. So x is equal to 0.050 liters. Let's see what our junior tutor said. This is a metric system conversion. 1 milliliter is equal to 1,000th of a liter, and a liter is equal to 1,000 milliliters. So to get liters from milliliters, you divide the amount by 1,000. Put it mathematically, 1 mil is equal to 0.001 liters, which is equal to 10 to the minus 3 liters, or 1 liter is equal to 1,000 milliliters. It's also equal to 10 to the 3 milliliters. For example, if you want to convert 10 milliliters to liters, you just use the conversion factor of 1 liter is equal to 1,000 mils. And then they did a similar example. 10 mils times 1 liter over 1,000 mils is equal to 0.01 liters. So this solution is correct. Okay, so I think that's all the time we have for this session. So if you like today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and the notification bell below. And if you wanted to submit a question of your own, then check out the links in the description. And also, if you like today's video, don't forget to leave a like and a comment. And also, if you wanted to share this video with all of your friends and classmates if they needed any help with chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye.